In today's class, let us consider this idea called torque. Um, Consider torque acting on a particle. Say we have a particle here. Its position vector from the origin is r. Okay, this is our particle. Position vector from the origin is r, and some force is acting on the particle along this direction. Okay. Then the torque due to this force is defined as torque tau is equal to r cross f, cross product between the position vector of the particle and the force acting on the particle. And direction of torque is, since it's a cross product between r and f, direction of torque is perpendicular to the plane containing the position vector r and the force f. Let us assume that this is xy plane. This particle is in the xy plane. So what is the direction of torque here? This is the direction of the vector r. So as usual, when we try to find out the direction of the torque, you rotate from the first vector to the second vector, from r to f. Okay, and you rotate the fingers of your right hand according to the right hand grip rule. Rotate the fingers of your right hand, four fingers of the right hand, from the first vector to the second vector. So from r to f. Then the direction of thumb gives the direction of the cross product. So here the direction of the thumb, the rotation, look at that, the rotation is in the anti-clockwise sense or counterclockwise sense. Okay. So when the rotation is in the counterclockwise sense, the direction of torque is in the plus z direction. Plus z direction. That is perpendicular and outward. Let us consider another situation. Okay, suppose the particle is here, and suppose the force is in some other in this direction. Then this is the direction of the vector r, and this is the direction of the vector force. So the rotation will be in the clockwise sense. Okay. So here, when you place the right hand at the common point between r and f, and you rotate the four fingers from first vector r to the second vector f, then the direction of the thumb is perpendicular and inward. So now let us see that the rotation from r to f is in the clockwise sense. So when the rotation is in the clockwise sense, the direction of torque is in the minus z direction. Okay. So it can be perpendicular and outward, or plus z direction, or perpendicular and inward, or minus z direction. In general, the direction of torque is perpendicular to the plane containing position vector r and the force f. Okay, now how do we write the magnitude of the torque? Okay, we can, as in the case of angular momentum, here also we can use geometrical method. Okay, this is the position vector r. This is the direction of the force. So this is the position vector r, and so then what we can do is we can take the perpendicular perpendicular distance from position the origin to the force. Let us call this r perpendicular. Okay, then the magnitude of the torque will be equal to r perpendicular into magnitude of the force. Magnitude of this perpendicular vector r perpendicular into magnitude of this force. So this is one way of writing. Take the perpendicular distance from the origin to the direction of the force, and magnitude of the torque is magnitude of this perpendicular vector r perpendicular and magnitude of the force. Another geometrical way of writing the magnitude is, getting the magnitude is, okay, this is the position vector R, force F. Now you can drop a perpendicular from the force to the position vector, which gives you the perpendicular component of the force, and the magnitude of the torque you can write as magnitude of R into magnitude of this perpendicular vector, F perpendicular. Okay, so the magnitude of the torque is in general R, magnitude of R into magnitude of F into sine theta, where theta is the angle between R and F. This is the angle theta. Okay, and this you can either interpret as R sine theta into F, this equation. You can either this interpret as R sine theta, which is R perpendicular, magnitude of R perpendicular, into magnitude of F. Or you can interpret this as F sine theta, which is F perpendicular, into magnitude of R. So that is two ways of writing the expression for torque. And the algebraic way of writing is just like we write any cross product in 3 dimensions using a determinant I, J, K. Components of the first vector is R, so components are X, Y and Z. And second vector is force, components are Fx, Fy and Fz. So if we evaluate this determinant, we get the magnitude of the torque. I mean magnitude as well as direction of the torque. So that is an algebraic way of getting the expression for getting the value of torque. Now torque in rotational motion is analogous to force in linear motion, but they have their own. They are not. They are only analogous. They have differences also. The main two differences between torque and force are force acting on a body is independent of the choice of the origin of the coordinate system. Whatever be our choice of the origin of the coordinate system, force will be the same. But torque acting on a body depends on the choice of the origin of the coordinate system. That means with respect to which origin we are measuring the torque. Why? Because in the expression for the torque, you have not only force but also the position vector of the particle. Okay, of a particle in the body. So that means if you change the origin, the position vector will be different, torque will be different. So torque depends upon the choice of the origin. And secondly, torque is always perpendicular to the direction of the force. Okay. Now, in the context of rotational motion, a body can experience in general both force and torque. But there are also situations where there can be torque but no force, and also there can be force but no torque. Okay, to illustrate this, let us consider the torque and force acting on a disc. Okay, consider a disc. Let us calculate the torque about the center of the disc. Okay, so let us say consider one situation where this is the radius of the disc R. So consider a situation where there is a force acting on this point, call it small f, and there is also force acting on the diametrically opposite point here, tangential force. Equal and opposite forces. So what is the resultant force acting on this disc? Resultant force is equal to 0. Magnitude of the resultant force is 0, but because these two forces are equal and opposite, let us calculate the torque at the center of the, with respect to the center of the disc. So first consider torque due to this force. This is the direction of the vector R. This is the direction of the vector R. So when you rotate from okay, the perpendicular distance from this point, the origin, to the force is nothing but the radius of the disc. Okay, so the magnitude of the torque due to this force is we get perpendicular distance into force. So R into F. What is the direction of this force? Let's find the direction of R cross F. R is in this direction towards right. Force is upward. So when you rotate from R to F, the rotation is in the counterclockwise sense. So R cross F will be in the plus Z direction. Right. So this will be in the plus Z direction. R cross F will be in the plus Z direction. So there will be so torque due to first force is RF in the plus Z direction. Now consider torque due to the second force. Here also the perpendicular distance from the origin to the direction of the force is again R. So the magnitude of the torque is RF. Let us see the direction of the torque. For this we have to take the direction of R, which is this. So direction of R to direction of F, the rotation is in this sense, clockwise sense. Sorry, counterclockwise sense. So again the force, if you apply the right hand rule, what you get is again the torque is in the plus Z direction. So the two torques are in the same direction, so we can add them. So the resultant torque is 2RF in the plus Z direction. So in this situation, the disc has a net torque, but there is no net force. Okay, now consider a second situation. Okay, this is a radius. Now here there is a force acting tangentially downward, and at the diametrically opposite point there is again an equal force acting tangentially downward. So there are two forces acting on this disc in the same direction. So the resultant magnitude of the resultant force is F plus F, 2F in the downward direction. Okay. Now what is the magnitude of the torque about the center? Here the direction of due to the first force. Okay, its magnitude is RF. Okay, because we have seen from the previous case perpendicular distance from the center origin to the direction of the force, the point of the force is R. But what is the direction of this torque? R cross F. Here the rotation is in the clockwise sense. So the torque is in the minus Z direction due to this force. And when you consider this case, this we have already seen, R cross F is this, the sense of rotation is anti-clockwise, so the torque is in the plus Z direction. So the torque due to the force on the right side, this will be RF in the minus Z direction, because the sense of rotation from vector R to vector F is clockwise, right? So this is minus Z direction, whereas the torque due to the force on the left side, this here the rotation from R to F is in the counterclockwise sense, so the torque is in the plus Z direction. So the net torque due to these two forces is 0. So this is a situation where there is a net force but there is no net torque. Now consider a third situation. Here a force is acting tangentially in the upward direction, and that's all, only one force is acting. So what is a net force? F. Magnitude of the net force is F in the upward direction, and we know what is the magnitude of the torque. Magnitude of the torque is RF. What is the direction of the torque? You are rotating from R to F, which is in the plus Z direction. So RF in the plus Z direction. So this is a situation where there is a force as well as a torque. So in general, in the case of rotational motion of a body, there can be force as well as torque, but there can be situation where there is no net force, as in the first case there is no net force but there is some torque. In the second case there is a net force but there is no net torque. In the third case there are both force and torque. Okay, so that depends upon the situation. And now let us consider I will take the space. consider a body in equilibrium. So what is the force and torque acting on a body in equilibrium? Okay, so consider a body at rest, which is in static equilibrium, let us say. Then if the body is in equilibrium, then the total force acting on the body, okay, so a body in equilibrium, a body at rest, let us say. So in this case, the total force acting on the body should be 0, and total torque acting on the, sorry, we have to use, so total torque acting on the body is also 0. So this is the condition for equilibrium. Total torque force should be 0 and total torque must be 0. And in the case of torque, we remember that torque depends upon the choice of the origin, right? So how do we calculate the total torque, about which origin, which point? But the point is that the idea is that we can choose any origin, okay, any origin on the body, because the total torque must be 0 about every point for a body in equilibrium. Okay, for a body in equilibrium, the total torque about any point on the body should be 0. So we are free to choose any origin on the body to calculate the torque. Okay, usually what we do is, the most convenient choice of origin is generally a point where several forces are acting. Okay, so we look at a body, we locate or identify the different forces acting on the body at different points, and to calculate torque, we choose a point where maximum number of forces are acting. Why? Because if we choose this point as the origin or the reference point for calculating torque, then there must be some 2 or 3 forces acting on that point. Let us say there may be some 2 or 3 forces acting on that point. If we choose that point itself as the origin, what is the torque due to the 2 or 3 forces acting at that point? 0, because torque is R cross F, right? So if you have at a point, you have some 2-3 forces, for example, consider a situation like this. You have some body, there are different forces acting on the body. Let us say at this point, point 1, you have a force F1. At this point 2, you have let us say 3 forces or 2 forces. F2 is acting in this direction, F3 is acting in this direction, okay, and you have another point 3, there you have a force, let us say, maybe I will write this notation, F2, F2 and F2 prime, okay, and at the point 3 you have a force F3, like this. So which point is convenient? So if this body is in equilibrium, total forces acting on the body must be 0. That is sum of vector sum of F1, F2, F2 prime, F3 should be 0. Total force should be 0, and total torque about any point in the body should be 0. About every point in the body should be 0. So you are free to calculate, and we can, if we try to calculate the force torque due to all these forces, we can choose any point as the origin. Not necessarily these 3 points, but any point in the body as the origin. But the convenient choice is this point 2. Why? Because if we choose point 2 as the origin for calculating torque, then immediately we see that the torque due to F2 and F2 prime will be 0. Because here the position vector is 0 itself. So torque due to forces acting at a point, if we choose that particular point as the origin, then there is no position vector here. The magnitude of position vector is 0. Therefore torque due to F2 and F2 prime will be 0. But about this point, there will be some torque due to F1, there will be some force torque due to F3. So we need to calculate only torques due to these two forces. Okay, if we choose point 1 as the origin, then we will be we should calculate the torque due to F1 will be 0, but torque due to F2, F2 prime and F3 will be non-zero, that we have to calculate. Okay. Similarly, if we choose point 3 as the origin, torque due to F3 will be 0, but we have to calculate torque due to F1, F2 and F2 prime. Now suppose we choose some other point other than these 3 points, then what is the situation? We will have to calculate torque due to all these 4 forces, F1, F2, F2 prime and F3. Okay. Now whatever be our choice of the origin, the total torque must be 0 if the body is in equilibrium. Okay, so in order to make our calculation easier, always a good choice is choose a point where maximum number of forces are acting. So in that respect, in this particular problem, best choice is the choice of the origin is point 2. Okay, so let us try to illustrate this situation for a body in equilibrium, how we calculate different forces and torques. Let's consider a particular problem. Okay, so this is a situation. Suppose this is the XY plane. Now a rod is bent in the form of a quadrant of a circle, and it is positioned like this. Okay, now this is ground, so one end of the rod is fixed on the ground, and this is some wall, so the second end is fixed on the wall, and this rod is at rest. Okay, the radius of this rod is pi r by 2. Now when it is bent in the form of a quadrant of a circle, it is bent into the form of quadrant of a circle of radius r. Okay, so the radius of this quadrant is r. Okay. Okay, so we want to calculate, this rod is at rest, that means it is in equilibrium, and this wall is a frictionless wall. Okay, this is a frictionless wall. The ground is not frictionless, but the wall is frictionless. So we need to calculate the force exerted by this rod on the wall. Okay, what is the force? Question is, what is the force exerted by the quadrant, we can say, or the rod on the wall? This is the question. We want to calculate that. Okay. So let us identify the different first let us identify the different forces acting on this quadrant. Okay. First of all, the force exerted by the quadrant on the wall must be equal and opposite to the force exerted by the wall on the quadrant. Okay. So at the point where the quadrant, this rod, is in contact with the wall, there must be a force exerted by the wall on the quadrant acting in this direction. Let us call this force as A, vector A. Okay, so there is a force acting here, normal to the surface of the wall, and since the wall is frictionless, there is no horizontal force acting there. Okay, now when you come to this point where the quadrant rests with the ground, it's in contact with the ground. Okay, there must be a normal force here. This is, let's call it normal force exerted by the ground on the quadrant, and there must be a tangential force. Let us call it B. Why? Because this ground has friction, so it must be exerting. See, this rod will be trying to move towards right when it is positioned like this. So this ground will be holding the rod by applying a friction tangential to the opposite direction. Okay, so this is it. So only on the ground there is a tangential force because there is friction. Since the wall is frictionless, there is no tangential force there. Now, so there are three forces now, but in addition, there will be the weight of the rod acting downward. So the weight of the rod will be acting downward at the center of mass of the rod. So what will be the center of mass of the rod? Okay, it will be this point. Okay, this point will be lying at an angle pi by 4 or 45 degree. Pi by 4 radian or 45 degree with the x-axis. So this is the center of mass of the rod, and the weight of the rod will be acting perpendicular or vertically downward, say W. So these are the four forces acting on the rod. Okay, so the four forces are force A, which is acting normal to the wall at the point where the quadrant is in contact with the wall. Okay, there is no horizontal force at this point because the wall is frictionless. So this is the point where it is acting. And at the point where the quadrant or the rod is in contact with the ground, there is a normal reaction force perpendicular to the ground, and there is a tangential force due to the friction of the ground. Okay, and this tangential force is the one holding the rod here. And a fourth force is at the center of mass of the rod, there will be the weight of the rod acting vertically downward. Okay. Now, when the rod is in equilibrium, total force must be zero. That means the total force must be zero in the horizontal direction as well as in the vertical direction. So, what is the condition for that? What are the forces in the horizontal direction? Force A is acting towards right and force B is acting towards left. So we can say A must be equal to B, or we can say the magnitude of A must be equal to magnitude of B. We can see that the directions are opposite to each other. Okay, so the magnitude wise, magnitude of A must be equal to magnitude of B. So A is equal to B, and also in the normal direction also, the vertical direction also, the total force must be zero. Therefore the force in the downward direction, which is weight, must be equal to the normal reaction. Okay, so these two conditions ensures that F total is equal to 0. Okay, now we need to calculate the torques due to all these forces. There are four forces here. So for that we need to choose an origin on the body. So there are different points on the body. Whatever be the choice of the origin, the total torque acting on the body about that origin should be 0. So what should be the best choice? If we look at the different points on the body, what should be the best choice? You have to choose a point where maximum number of forces are acting. Then we don't have to worry about the torques due to these forces. They will be automatically 0. So if you look at this body, now we can see that the best choice is this point, because there are two forces acting at this point, a horizontal force B towards left and a vertical force N in the upward direction. So if you choose this point as the point where the rod rests on the ground, if you choose this point, then the torques due to these two forces, force B and force N, will be automatically 0 because the position vector is 0. So we need to calculate only the torques due to the other two forces, A and W. So this is our good choice. So let me mark this point as let us say O. This is the origin. So first let us calculate the torque due to the weight of the force, which is equal to the weight of the body. So let me redraw this figure for that. This is our quadrant. This is the center of mass, and the force is W. This is our origin. So what is the torque due to this force? So for that we need to find out the perpendicular distance between this force and the origin, and the perpendicular distance is this one, this much. Let's call it L. Okay, so the magnitude of the torque is, let me call it tau 1. It is perpendicular distance L into force. Now what is the direction of this torque? To find the direction of this torque, we need to look at the direction of r cross f. What is the position vector from the origin to the force? So the position vector from the origin to the force is this. Okay, and this is the direction of the position vector. Let us call this position vector as r1. So the direction of the torque is direction of r1 cross w. So this is the direction of r1. When you apply the right hand rule, you rotate from the first vector r1 to the second vector, which is w. The rotation is in the counterclockwise sense. So the direction of the torque is in the plus z direction. Plus z direction. Now consider the second force, which is A. So again I am redrawing. Okay, this is the force A, and this is our origin. So what is the, first of all, what is the magnitude of the torque? Let's call it as tau 2. What is the magnitude of the torque? It's a we need to find the perpendicular distance between the origin and the force. So the perpendicular distance between the origin and the force is this distance, which is radius of the quadrant r. This rod is bent into a quadrant of radius r. So the magnitude of the force is simply r into A. What is the direction? To find the direction, we should know what is the position vector from the origin to the force. So the position vector from the origin to the point at which the force is acting is this one. This is, let us say, the position vector is r2, and the direction of the position vector can be extended like this. This is the direction of the position vector. Okay, so what is the direction of the torque? It's the direction of r2 cross A, and for this you again rotate from r2 cross A. Now this sense of rotation is clockwise. That means the direction of the torque is in the minus z direction. Minus z direction. So if you take plus z direction as positive, okay, we can write the total torque as tau 1 plus tau 2. But tau 1 we treat as positive, tau 2 we treat as negative because its direction is opposite. So this is the net torque or total torque acting on the body. Now since the body is in equilibrium, okay, the body is in equilibrium, total torque must be 0. So total torque equal to 0 implies L into W minus R into A should be 0. So what is the expression for A? We get L into W divided by R. Okay. Now from this from this figure, let us look at this figure, original figure. If you extend this direction, you have a right angle triangle here. This is R, hypotenuse. Therefore this side is r cos pi by 4. This is r cos pi by 4, right? And from here to here the distance we have marked as L. Okay, whereas the total distance from this point to O is R. So the point is that from the figure, R is equal to r cos pi by 4 plus L. Therefore L is equal to r minus r cos pi. What is cos pi by 4? 1 by root 2. So r minus r by root 2. Okay, now if you work out this, you can check this value. What you get is 0.293 R. Okay, so L we can rewrite in terms of R. So in the expression for A, L is 0.293 R into W divided by R. So R will cancel. So the expression for the equation for A, the value of A is 0.293 W. That is the result. The force exerted by this rod on the wall, this point, which is same as the force exerted by the wall on the rod, is its value is 0.293 W, 0.3 times the weight of the rod. Okay. So here we have used the idea that this rod is in equilibrium, which means that the total force is equal to 0 as well as total torque is equal to 0. Okay. And we have chosen this point as the origin. Now, by extending this example, you can do a homework. You can choose another point as the origin. For example, you can choose this point as the origin, the point at which the rod rests on the wall as the origin. Okay. Then also the total torque at this point should be 0. About this point should be 0, and we should get the same result, that A is equal to 0.293 W. So you should try that. You calculate, choose this point as the origin, okay, and calculate the torque due to. So immediately you can see that if you choose this point as the origin, torque due to force A is 0, but you need to calculate torque due to W, torque due to N, torque due to B. Okay, you need to calculate that, and then you try to find out the expression for A. And in this case, torque due to A will be 0, but torque due to B is non-zero. And remember that A is equal to B from the condition for total force is 0, A equal to B, and also remember that N is equal to W. Okay, so you use these results, and you calculate the torques due to the three forces W, N, and B at this point, choosing this point as the origin where the rod rests on the wall, and you repeat this calculation. That will be very instructive. Look at the direction also, okay, because torque, you have to worry about the direction also. So some torques will be positive, some will be negative, and you can find out the result. Okay, so let us stop now. So what we have discussed in this class is the definition of torque, okay, R cross F, and its magnitude you can calculate as perpendicular distance from the force, R perpendicular into force, perpendicular distance from the force into magnitude of the force. That gives the magnitude of the torque, and the direction of torque is obtained by finding the direction of R cross F. If your rotation of your fingers from R to F is in the counterclockwise sense, the torque is towards you, perpendicular and outward, or plus z direction we say, with the idea that this board is in the xy plane. If the rotation is in the from R to F is in the clockwise sense, then the thumb will be pointing perpendicular and inward, or in the minus z direction. Okay, so the direction of torque is perpendicular to both R and F. For that, you need to use the right hand rule. And okay, well, we know that torque is analogous to force. Torque in rotational motion is analogous to force in linear motion, but these two quantities are different. Torque and force are different. Force is independent of the origin of the coordinate system, whereas torque depends on the choice of the origin, and torque is perpendicular to the force. Okay, we also know the algebraic method of writing the torque using the determinant, right? This type of a determinant, ijk, xyz, fx, fy, fz. Okay, and in rotational motion, there can be situation where there are both force and torque are present, but there can be situation where force is present, torque is 0, torque is present, force is 0. Okay, and if a body is in equilibrium, okay, then the condition is that total force is equal to 0 and total torque about any point should be 0. And we have seen this example as an illustration of that. Okay, let us stop now.